This is the board out of my current Mailbox notification system, which is powered by a 7.4 volt lithium-ion battery. Today I'm going to take a look to see if I can design a different board, maybe even use a different battery to get more than the 3 to 4 weeks I'm getting out of the current system. So hang around. Hi, welcome to Res and Chem Tech. About 2 years ago, I built a mailbox notification system that uses Home Assistant and Google to make announcements in the house when the mail has arrived. But despite using a 7.4 volt lithium-ion battery, where I thought I was going to get anywhere from 6 months to a year out of the battery, I found I was only getting 3 to 4 weeks in actuality. And it was getting real annoying having to go out and replace the battery all the time. So while we'll briefly take a look at the current board design, this video is really not going to be about the mailbox notification system. If you're interested in how I got that to work with Home Assistant and the Google Voice notifications, I'll leave a link right up here. But really, we're going to be looking about how might we be able to get longer battery life when using an ESP32. So this is the original board design. And just to give you a brief overview of this, obviously we're using an ESP32 chip, and we're using an ESP32 for its ability to go into deep sleep and remain in deep sleep until it's awakened by an external event on one of its GPIO pins. Now, while the ESP32 chip itself runs off of 3.3 volts, the board runs off of 5 volts. And I wanted to use a 7.4 volt lithium-ion battery with the idea of getting longer battery life. And when fully charged, this is about 8 volts. So my belief at the time was I needed to take this 8 volts and step it down to 5 volts to run my board. So what I ended up putting in here is a small step up, step down voltage regulator that will take anything from about 2.7 volts all the way up to around 11.8 volts and put out a constant 5 volt signal. So I was going to be able to take my 8 volts, step it down to 5 volts to run to my board. Now, I also created a small voltage divider here that would step down that 8 volts down to a maximum of 3.3 volts to feed into an analog pin so I could keep an eye on the voltage. The reason I wanted to keep an eye on the voltage is because I did know that these lithium-ion batteries could not be all the way drained or you would actually destroy the battery. That actually happened twice. I'll come back to that in a minute. What I didn't realize, and thanks to one of my viewers for bringing this to my attention, since this runs off of 3.3 volts and the board runs off of 5, there's already a voltage regulator on board, and this voltage regulator would easily handle the 8 volts from this. So this step up, step down regulator is not needed. Now, again, only getting 3 to 4 weeks, obviously something is continuously drawing power even when idle. Odds are it was probably the step down, step up converter, could be my voltage bridge, or this ESP32 board isn't going into the low level of deep sleep where it's only drawing microamps. So we're going to take a look at a couple different designs, and we're actually going to see if we can figure out where the battery drain is occurring. So I lived with the system for about a year, going on a year and a half, going out every 3 to 4 weeks and replacing the battery. But in the process, I also destroyed 2 battery packs. As I mentioned earlier, you can't over-discharge these batteries without destroying them. So each 3.7 volt lithium cell, ideally you don't want to take it much below 3 volts, maybe 2.7. 2.5 you might even get away with, but you're probably going to affect the longevity of the battery. But much below that, and you're going to destroy the battery, which is what happened in my case because I was out of town on 2 different occasions when that voltage dropped. And once it drops below 5 volts, that pull-up regulator was drawing even more power. And within the matter of a 24-hour period, the battery was drained all the way down to about 1 volt, and they were destroyed. So if I'm going to rebuild this controller, in addition to trying to extend the battery life, there's a couple other goals I would like to have. First of all, I would like to see if I can make the controller size smaller. And by doing that, I can use one of these ESP32 minis instead of the full-size Node MCU, which means I should be able to go down from a controller of this size to one about half the size. The other thing that I would really like to have is a low voltage cutoff to protect and save those batteries from being completely drained. So those are the 3 things I'm going to try to build and see how well I can accomplish. Extend the battery life to a minimum of 3, preferably 6 months. Make the overall size of the controller smaller. And 3, have some kind of voltage cutoff that's going to protect the battery from being drained to the point of no repair. So I've decided I want to take two different approaches to trying to extend this battery life. For the first one, I'm actually going to use a battery shield, which is made for a Wemos D1 Mini, but it will work with our ESP32 mini board. Part of the reason I want to try this is I want to see if this actually has a low voltage cutoff that will help protect the battery. But to use this, I am going to have to drop down to a 3.7 volt lithium ion battery, a single cell, because this won't handle the 7.4 volts. In the second approach, I'm going to go ahead and stick with this battery, but I'm going to eliminate that voltage regulator that I had in the original version. And we're going to be able to compare the two of those and see which one might be a better solution. But first, I want to take a little closer look at this battery shield. Okay, so what I want to do here is I want to test my D1 Mini, the power hat. A couple of things. I want to make sure I'm getting a constant 5 volts out, which is going to power the ESP32. And right now I'm giving it 4 volts, which would be about the full charge on the lithium ion battery. But I also want to know if there's a low voltage cutoff that's going to cut off the supply to the board so it doesn't continue to draw a battery. So what I'm going to do is I'm going to slowly lower the voltage here, make sure that my 5 volts holds constant, and if there comes a point where there's a cutoff, because I couldn't find any documentation. I found some comments that said that it cuts off around 2.5 volts, but I want to test that out and try. So we're going to slowly lower the voltage, which is going to simulate our battery draining. And ideally, this would cut off at about 2.7 volts, but I could probably live with 2.5 if that's what really happens. Well, there's our 2.7, and we're still drawing a constant 5 volts. Let's drop this down to just a bit more. Get it down to 2.5. Yep, and it looks like there it goes. So it's at 2.4. Or did it just a smidge? Okay, so coming back up at 2.6. So right around that 2.5. You're seeing the voltage slowly drop because there's a capacitor on there that's holding a little power, but it looks like that's draining, and it should settle into right about 2.5 volts. So the good news is, and of course our board won't power up at 2.5 volts. So, the good news is it does look like it has a cutoff. If I increase the power, so in other words, I'm going to simulate plugging in a fresh battery. Yep, it comes right back up to the 5 volts. So that's good. So I have confirmed that this does give a stable 5 volts down to about 2.5 volts on the battery. So I think that's the two different approaches I'm going to take. I'm just going to throw this together on a breadboard right now to try to determine which design might be better and then build my final controller based on the test results. So here are the two final board designs. Down here on the bottom is the one for the 7.4 volt battery. We're going to feed the 7.4 battery directly into the ESP32, but the onboard voltage regulator will take care of knocking that down to the 5 volts. We've got our voltage divider here, which is using a 68K and a 47K resistor. So it'll take the fully charged about 8 volts of this battery, knock it down to about 3.27 volts that we're going to feed into an analog pin here to measure our voltage on each cycle. And these are our two leads for our read switch, that every time it opens, it's going to wake up the ESP32 and we'll measure the voltage. Up here is the 3.7 volt setup. Again, we're using a battery shield on the top. For that, we're going to feed the battery directly in here. And I actually soldered 2 wires right on the back side of this to feed down to the voltage divider here, which is using a 15K and 68K. It'll take a fully charged about 4 volt battery and knock that down to about 3.28 volts. Once again, to feed onto an analog pin for measurement. Our 2 leads for our read switch, which again is going to wake up the board to take our voltage measurement. So that's the final board design. That's what we're going to go with. At this point, we're ready to start the test. So next I need to figure out how to test these batteries and these board setups in an accelerated fashion so I didn't have to wait months to see the results. To do that, I've decided to break the test into 2 separate parts. One is when the ESP board is active. So that would be twice a day on average, once when the mail gets delivered, once when it gets picked up, and the board would be awake for 1 minute each time, so about 2 minutes a day. Now, the second half of the test is what happens with that battery during the other 23 hours and 58 minutes that it's basically in deep sleep or idle. We're going to take a look at the active part of the board in the first test. So this is going to be our Mailbox simulator. What I've got is some Arduino code on a Wemos D1 Mini that's going to drive a couple of servos, and it's going to be set up so that once about every 5 minutes it's going to simulate opening the mailbox. Okay, so there the mailbox opens. Once opened, it's going to remain open for about 10 seconds, and then it's going to close the mailbox, which would simulate mail being delivered. Now I picked to do this every 5 minutes because that gives me 12 per hour, and that's going to be equal to about 1 week of mail delivery, mail pickup. So just to give you an overall view as how we're going to be capturing these voltages, again, here are those servos that are going to be opened once every 5 minutes by Wemos D1 Mini. When those open, it's going to trigger the ESP32s to wake up. And using ESPHome, after about 30 seconds or so to give the voltage a chance to stabilize, it's going to measure the voltage coming off the analog pins of these chips. When it does that, it's going to publish an MQTT message in our Home Assistant broker. Over here, running on a Raspberry Pi, will be a Python program that sits and listens for those MQTT messages, and every time it receives one, is going up to write a rote to a MySQL database capturing the number, the cycle number, and the measured voltage. Now, in addition, since the voltage off these analog pins aren't really exact, it's really just a relative voltage, I'll be taking direct measurements of the batteries themselves once every 4 hours. So I'm going to start the system and let it run for about 26 hours. Now, the reason I picked 26 hours, if each week is 12 activations, that's going to simulate about a week of mail delivery and mail pickup. So the 26 hours is going to be equal to about 26 weeks of active time, which is about a half year. And after we've done the active time, then we'll take a look at the battery during idle time. So I'm going to go ahead and test the starting voltage of the fully charged batteries, just so we know what point we're starting from. And if we look at our 3.7 volt lithium ion, we're at about 4 volts fully charged, which is correct. That's about where it should be. And then if we take a look at our 7.4 volt lithium ion battery, again, we can see we're right about 8 volts, which is where it should be. So we've got 2 fully charged batteries to begin our test. So while this test is running in the background and I've got some time, we'll take a quick look and just double check on the Python and MySQL side of things. Take a look at ESPHome and describe a little bit more in detail about how I'm using that. I'll also talk about how I'm going to set up and conduct the second half of this test to measure the battery over time when the ESP32 boards are in sleep mode. I'll cover the various sleep modes of the ESP32 as well, but if you're not interested in any of that, feel free to use this timeline along the bottom of the video or the links in the video description to jump straight ahead to the final test results and the conclusions that I reached. And there's really nothing to see here other than the Python program running on the left-hand side of the screen, and the right-hand side of the screen shows where the SQL Server results are being reported. So everything seems to be working fine on that end. If we take a look here at Home Assistant, we can see those values are also being sent out and recorded by Home Assistant through ESPHome. Okay, so let's also take a quick look here at ESPHome. This is our mailbox with our 7 volt battery. Mailbox new is the one 3.7 volt battery. And what you'll see happen here in just a second, the servos just fired, opened, and you see both of these now just bounced online. Currently, both of these are set to stay awake for 60 seconds. That's really a pretty long time. Ideally, you would only have it open for maybe 10 seconds, just long enough to send the voltage. But in the testing I had with my other battery, or I guess real world example, it takes a while once the thing wakes up to be able to connect to the Wi-Fi, especially because we're out there at the mailbox, which is a fairly weak Wi-Fi signal. In addition, it also has to connect to the Home Assistant API. That can sometimes take anywhere from 30 to 45 seconds. And the problem is if it doesn't complete that, after a few tries, it basically sets the equivalent of a watchdog. It says there might be something wrong, and then it's going to go back into fail-safe mode, which means it's going to quit functioning. So I've found that as nice as it might be to cut this time way down to maybe 15 seconds of wake time, I've found about 60 seconds is about the minimum. Plus, if I do need to flash new firmware, I do have a command to take it out of shutdown mode, but it has to be awake long enough for me to issue that MQTT command. So yes, if I could go from 60 seconds to 30 seconds, you would have to figure that I'm going to double the amount of time the battery lasts. But I've found about 60 seconds, at least for me, to be the minimum. And now you can see that both these now have returned back to offline status, and they'll sit there until our next cycle fires in 5 minutes. Okay, the first 26-hour test is complete, and that includes me getting up twice in the middle of the night to take direct battery readings at 4-hour intervals, which is another reason why I only ran this for 26 hours. But now I have to set up and do the second part of this, and that is to measure that battery draw over time for the 23 hours and 58 minutes a day that it is sitting idle. So to do that, I've recharged both batteries back to their original starting voltages, which is 8 volts and 4 volts, hooked them back up to the system, and the only difference is this time we're simply not going to open those servos. We're just going to let them sit. And I'll be taking direct battery readings with my multimeter from the battery every 12 hours. I plan on letting that run for about 4.5 days, and then come back and take a look at those results. I'll save all the results for the end. Again, use the links if you want to jump straight forward to that. But I really suspect that there's going to be a much bigger battery drain during that idle time, even though it's supposed to be in low power mode, than when the boards are active. And I think there are a couple of reasons for this, which I'm going to cover next. So first off, even though we talk about the ESP32 in deep sleep, the ESP32 actually has multiple sleep modes. If you take a look at these diagrams that I got from lastminuteengineers.com, up here when the ESP32 is active, which basically means everything on it is running, it's going to show a power consumption, we'll call it 200 milliamps. Well, the first stage of sleep is something called just modem sleep. Basically what it's doing there is it's turning off the radios, and our power consumption drops down to somewhere around 10 or 15 milliamps. Then there is light sleep, which again turns off all of the radios and external devices and pauses the core memory of the ESP32. That drops us to 0.8 milliamps or 800 microamps. And then finally, deep sleep, and I guess this is supposed to mean deep sleep, turns everything off except for the coprocessor and the real-time clock and peripherals, and knocks this all the way down to 10 microamps. I'm going to assume that ESPHome is activating this deep sleep, but I really don't know for sure whether it might actually be putting the ESP32 into light sleep. So I'm going to guess we're somewhere under a milliamp when we put it into deep sleep via ESPHome. Unfortunately, I don't have a way with the equipment that I've got to measure things down in the microamp range. And note that these power readings are actually just for the ESP32 chip itself, but we're not using the raw chip. Instead, we're using a development board, and there may be additional components on here that are consuming power. For example, I've read that the UART chip, which is the USB to serial chip, continues to run even when the ESP32 chip is in deep sleep. In addition, almost all of these boards have an LED indicator light. Now, I always desolder that light and remove it so it's not using power, but that would also take up power, and that stays on even when the board is in deep sleep. So we have additional components on this board that might be consuming anything from small to large amounts of power, even though our chip is in deep sleep. Next, there are a couple of additional things in my particular board designs that might be using power. This is that battery shield. Again, the fact that this is stepping up a 2.7 volt battery up to 5 volts to run the ESP32 board, you got to assume that this is drawing more power, at least when active. But what I don't know is when the ESP32 goes into deep sleep, whether this board continues to draw any power from the battery or not, either through the voltage regulator or capacitor or other components. So we really don't know. That's part of what I hope to find out in our long-range idle test. And both of my designs use a voltage divider so that I can keep track of the battery voltage over time. Now, this voltage divider is also going to draw some continuous power. But by using high-value resistors, I can try to keep the amount of power low. So in this case, we're looking at the 4 volt at about somewhere around 48 microamps up to 70 microamps on the 8 volt. So try to do a little bit of basic math here. If we consider from our chart before that when the ESP32 is active, it's going to pull about 200 milliamps. However, when it's in its sleep state, ideal situation, 10 microamps for the chip, 70 microamps for that voltage divider, and I'm going to throw 120 microamps in there just for other components. Really, it's just to make my math easier. So we're saying it's Theoretically, when it's in deep sleep, it's using 200 microamps, 200 milliamps when the ESP32 is active. So we look at that over a given 24-hour period, the ESP32 is active for 2 minutes, but it's inactive for 1,438 minutes, which is 720 times longer, but it's at 1/1000th of the power. Theoretically, when we're running our idle test, we ought to see performance that is nearly as good as, or maybe even slightly better than we did in the active test. And if we don't, if the performance is worse, then we definitely know we're drawing more than the theoretical 200 microamps when at rest. So I've now completed 5 days of running the battery at idle, checking the voltage every 12 hours. So we're finally ready to take a look at the results. So first we'll take a look at the simulated active time. This would be the time that the ESP32 was awake and sending data. And if you remember, we did that once every 5 minutes for 26 hours, which would simulate about a half year. On the left-hand side here, you can see the voltage that was recorded by the analog pin through our voltage divider. And on the right-hand side is where I actually took a direct battery measurement every 4 hours throughout the 26-hour period. And again, with the analog pin, you can see there's a little bit of noise there, which is to be expected, but it takes to about 24 hours before we even drop the voltage down enough that it can be registered with the analog pin. If we look at the direct measurements, we'll see that over the 26-hour period, again, just simulating the opening and closing of the mailbox, we've lost maybe 200 millivolts, maybe even a little less with the 7.4 volt battery, and we're still not even down to the 3.7 or the 7.4 voltage of the battery itself. So in terms of just being able to wake up and send that data, there's no doubt that the battery could definitely last 6 months or maybe even a year. But now we have to take a look at that idle time. That's that 23 hours and 58 minutes a day that the ESP32 is sleeping and the system is idle. And if you take a look at this, over here is the direct measurements that I made every 12 hours for 5 days. And again, you can see what doesn't look like a whole lot of battery drop. If you extrapolate those results, and again, this is going to make a really broad assumption that that's going to be linear and that it doesn't tank and drop off at some point in time. But even if you assume linear, you see that after about 52 days, we're already down to right at our bare minimum of our 2.5 volts for our 3.7 volt battery. Really, again, that 2.75, maybe 42 days. The 7.4 volt battery does a little bit better, but I would say that probably maybe 60 days tops. And again, this does not include any wake time, which we know is pretty small in comparison. But so while it seems like we've made a little bit improvement over the maybe 24 to 30 days I was getting before, it's still nowhere near even the 3 months or ideally the 6 months that I'd hoped to get out of the system. So while my results are actually a little bit disappointing, I had really thought that maybe by getting rid of that step up, step down voltage regulator, I might be able to get at least 3 months out of the battery. It just doesn't seem it's going to be possible, at least not with these developmental boards and the lithium-ion batteries. I just think there are too many components on here that are drawing too much power even when the ESP32 is in deep sleep. Now I have restarted my battery test again, and this time I've even removed my voltage divider. I think it might make a little bit of difference, and I'll list it down, add something down to the video description if I find anything significant. Again, the drawback to that is now I have no way to monitor the battery over time, and it would be even that much more important to have some kind of low voltage cutoff system in place. So I just don't think that the ESP32, at least the dev boards, are going to be a viable solution unless you want to do something like adding solar power to keep the battery charged. And again, that's more wires and more things mounted on the mailbox, and chance of damage or theft to the solar panel. It's just not the route I want to go. And of course, if you have the skills and the knowledge, you could of course try to build something with the ESP32 chip by itself, your own PCB design, maybe eliminate some of these other components. I'm not an electrical engineer, and people start talking MOSFETs and diodes and transistors and my eyes glaze over. Again, I try to stick to somewhat fairly basic electronics, so that's not really a viable option for me. So really what you're looking at is maybe a different type of technology. And for about the past 6 months or so, I've actually been using Zigbee on my mailbox, just basically a simple Zigbee door or window sensor. The nice thing about this is it. No additional wires, no controller. This just goes inside the mailbox. But that's also the other problem with this. It goes inside the mailbox, a metal mailbox. And you close the lid, you can imagine what happens to the signal. So when I first started trying it, it would stay online maybe 2-3 days before it would drop off. The signal was really, really weak. And again, my Zigbee hub is really just inside the front door. It's fairly close to the mailbox. But even then, closing that metal lid, Faraday cage, nothing's getting in, nothing's getting out. So I actually did something that goes against one of my main rules. I actually made a small modification. Yep, I actually put a small hole about the size of a pencil in the back of the mailbox, and that surprisingly has made major improvements. And it will still occasionally drop off the network. Usually it's during something like heavy fog. It really seems to cause a problem. Sometimes it comes back on the network, sometimes it doesn't. But it actually has been an improvement over going out and replacing the battery every 30 days. So, I may have to look at something like the long-range WAN or LoRa, if you're familiar with that, maybe some kind of external antenna, but I just don't think that I'm going to be able to make much more improvement over using the ESP32 with a lithium-ion battery. So while the end results might not have been what I hoped for, I guess at least did save me of going through the process of actually building the controller and installing it back out there on the mailbox again, and then just learning in a month and a half or 2 months that I wasn't going to get the battery life that I expected. If you have any other thoughts or ideas, please feel free to share them down in the video comments. Otherwise, I'm going to bring the video to a close. As always, I'll ask if there's anything that you liked or you found helpful. Please go ahead and hit that like button. That lets both me and YouTube know you'd like to see more videos like this. And if you would like to see more of my videos, hit that subscribe button and ding that little bell icon if you want to be notified when I release new videos. As always, I'd like to say thank you for watching, and I hope to see you soon.